All right, so as Grace mentioned, we are Rheosense, a market leader in the biotech industry. Our headquarters are in Silicon Valley. Our claim to fame is the patented VROC technology, Viscometer Rheometer-on-a-Chip, and this is used by our Fortune 500 client base. So I'm going to introduce the team here at Rheosense. So we have Grace Bake, our Marketing and Sales Director, Lulu, our Technical Specialist, and then our Applications Engineering team consisting of Ivan Akrimachev, David Nieto, and me, Ryan Cohn. So today I'm going to be talking about VROC initium, advanced measurement features, and the added advantages of automatic viscosity measurements. So as an outline of the presentation, I'm going to give a brief overview of VROC technology. I'm going to talk about why we need automated viscosity fingerprinting. Then I'm going to cover some of the standard features of VROC initium, and then I'm going to get into the more advanced features of the initium unit. And this includes automatic measurement, sample retrieval, and performing automated temperature sweeps. And then finally, I'm going to give a summary of the applications. So VROC, or Viscometer Rheometer-on-a-Chip, is a hybrid of microfluidics and MEMS technologies. So we have a precision glass microflow channel that's equipped with a MEMS sensor pressure array, or MEMS pressure sensor array that records the viscosity measurements. And some of the advantages of VROC technology is that you can measure absolute viscosity with a precisely controlled shear rate. You can get measurements with very low sample volumes, as little as 12 microliters. You have a wide dynamic range in shear rates from about 1 inverse second to higher than 1,000,000 inverse seconds. You have flow through the channel rendering high throughput experiments, so you can gather a large amount of data in a small amount of time. You also have very good repeatability, as good as 0.5% of the reading. So this is an overview of how the VROC technology works. When you have flow through the microfluidics channel at a precisely controlled shear rate, there will be a linear pressure drop in the flow channel. So the pressure drop correlates to the shear stress at the wall of the flow channel. And then the shear rate of the fluid is known because the flow rate is controlled. So the shear rate corresponds to the flow rate and the channel geometry. So then the dynamic viscosity is simply calculated by dividing the shear stress by the shear rate. So now I'm going to talk about why we need viscosity fingerprinting. So the properties of samples are dependent on many different factors, such as concentration, pH, buffer type, etc. So in order to gain a complete understanding of how your samples will behave, you need to gather large amounts of data under different conditions. So with the initium, you can set up automated viscosity fingerprinting experiments to characterize the viscosity of your samples under many different conditions. And this is particularly useful for measuring the viscosity of your samples, which can be used to determine the injectability of pharmaceuticals, molecular size and formulation, and the stability of samples under different conditions. So now I'm going to introduce the VROC initium. So this is our high throughput, fully automated viscometer or rheometer. Because it is based on VROC technology, it can measure samples with very small sample volumes, as little as 12 microliters. You can use the initium with a 40 vial rack or 96 well plate to measure samples with high throughput, measure very large amounts of samples. But because it is based on VROC technology, you have precise control over the shear rate and temperature of experiments, allowing you to conduct shear rate sweeps and temperature sweeps between 4 and 70 degrees Celsius. And then you also have independent control over the sample tray temperature, so you can keep temperature-sensitive samples refrigerated while performing measurements at higher temperatures. So this is the layout of the initium unit. So as you can see in the bottom right corner, you have the 40 vial rack or 96 well plate. And this allows you to load all of your samples at once and then leave the unit unattended. And after it finishes a certain measurement, it can automatically load the next sample so that you don't have to touch it. In the middle of the unit is the heart of the viscometer where the measurement actually takes place. So the samples are loaded into the syringe using the auto sampler, and then after being loaded into the syringe, the sample is pumped through the VROC chip where the viscosity is actually measured. Then on the left of the unit, we have our cleaning solvents. So after every set of measurements, the initium automatically cleans and dries itself so you don't run into the problem of contamination or incompatible samples. So this is a truly fully automated viscometer. So now I'm going to talk about the applications of the initium. So as I've mentioned, it is a high throughput viscometer. You can test many samples unattended. You can measure the viscosity of your samples, which has several distinct applications. So one of the more important applications in biotech is injectability. If you characterize your samples at very high shear rates, you can determine if they're appropriate to use in pharmaceuticals, if they can be injected in a patient. You can also look at protein stability to figure out under what conditions your proteins are stable and what conditions cause them to denature. You can also look at the kinetics of chemical reactions. You can mix different chemicals and measure the viscosity to determine if a reaction is occurring, the equilibrium concentrations of all of the reactants and products, and other aspects of the chemical reaction. You can also determine solubility of different chemicals by mixing them and measuring the viscosity to determine if there is a single phase or a multi-phase solution. And then finally, if you conduct multiple measurements of very dilute solutions, you can measure the intrinsic viscosity of your samples. And this will correlate to the hydrodynamic radius and the molecular weight. So it allows you to characterize molecular properties of your samples. So I'm going to cover the standard features of the initium. So as it is based on VROC technology, it is compatible with samples with a wide range in viscosities from about 0.2 centipoise to 100,000 centipoise, or 1,000 centipoise if you're using the auto sampler. And you can conduct measurements at a wide range of shear rates from 1 inverse second to 1.5 million inverse seconds, or 135,000 inverse seconds if you're using the 100 microliter syringe. So the standard functionality allows you to rank your samples by viscosity at precisely controlled shear rates and temperatures. And as well as conducting single measurements, you can also measure the viscosity fingerprint of your sample, the viscosity versus the shear rate, or viscosity as a function of temperature. And then finally, you can estimate the injectability with viscosity measurements at very high shear rates. So if you're interested in learning more about the standard functionality of the initium, we actually have 2 previous webinars on the standard functions. And these can be found at rheosense.com/viscosity-webinars. So the first standard feature is that you get repeatable, accurate measurements. So the as it is based on VROC technology, you can expect that measurements with the initium are repeatable to 0.5% of the reading, and they're accurate to about 2% of the reading. So in the top left, we have a graph representing multiple measurements of distilled water. And each of the segments of the graph represents a different measurement. And as you can see, all of the segments are very consistent. So the measurements for water were very repeatable. And then below the graph, we have tabulated values for measurements with different NIST certified viscosity standards. And the measurements, for all of the measurements, the difference between the initium's measured value and the reference value is well within the specification limit of 2%. So this demonstrates the accuracy and repeatability of the initium. So the second standard feature is that you can conduct measurements with very small sample volumes. So in this experiment, we measured the viscosity of isopropyl alcohol at about 24 degrees. And we used a very small sample volume. So as you can see from the graph, the first 8 or so microliters are the priming volume, where fluid is filling the path leading up to and including the chip. And then after the fluid fills the chip, it only takes a few microliters to measure the viscosity value. So the total volume of this measurement was about 12 microliters. And as you can see, the measured value agrees very well with the reference viscosity for isopropyl alcohol at this temperature. Okay. And then the third standard feature of the initium is viscosity screening. So this allows you to measure the viscosity as a function of concentration of different protein solutions. So as you can see from the data, at lower concentrations, the viscosity of these different protein solutions can be predicted very well with the hard sphere model. However, above a concentration of about 100 milligrams per milliliter, the viscosity values start to deviate from this ideal model, especially for immunoglobulin G in phosphate buffer solution. So this is why having the ability to actually measure your samples under the conditions that you're going to use them in is very useful, because these theoretical models don't always accurately represent the viscosity. Then the fourth standard feature is you have viscosity measurements at precisely controlled shear rates. So this is particularly useful when characterizing non-Newtonian fluids where the viscosity changes with shear rate. So this is important for applications such as injectability, where the samples will be subjected to very high shear rates as they are injected into a patient. So in this example, we tested xanthan gum, which is a shear thinning fluid, and we found that as the shear rate is increased from about 100 to 1,000 inverse seconds, the viscosity drops almost an order of magnitude, from about 100 to 10 millipascal seconds. And then finally, the last standard feature of the initium is that you have precise temperature control. So this allows you to characterize the thermal behavior of your samples. And here we provided several examples of different protein solutions with different buffers and different concentrations, all measured at different temperatures. So it really does allow you to get a large set of data to really understand the behavior of your different samples. All right, so now that I've gave a brief overview of the standard features of initium, I'm going to start talking about the more advanced features. So the first advanced feature of initium is automatic mode. So normally when you are conducting viscosity measurements, you have to specify the shear rate at which the measurements are to be taken. However, since the viscosity of your sample is not always known, it can take a while to determine the appropriate shear rate, which can take time and resources. So with automatic mode, the initium will begin pumping fluid through the chip and use the pressure values in the chip to determine an appropriate shear rate to get a good measurement, so that you don't have to input the shear rate. And this is very useful for quickly testing a variety of samples with different viscosities. It's useful for testing samples at different temperatures, since the viscosity of most samples is heavily dependent on temperature. It also just makes measurement simpler. The same measurement protocol can be used with almost any sample, because you know that your shear rate will always be chosen well. So in this example, we measured the viscosity of a standard, or a viscosity standard mineral oil between about 20 and 50 degrees. And as you can see, the change in viscosity is significant. So each of these tests would be conducted at a different shear rate. But because we used automatic mode, we didn't have to figure out beforehand what shear rates to use. We just ran the experiment, and the initium determined the best shear rates automatically. So the next advanced feature I'm going to talk about is sample retrieval. So normally, after being pumped through the chip, a sample is discarded in the waste stream. However, with sample retrieval, instead of being directed into the waste stream, a sample is pumped into the reservoir. And then if the test syringe runs out of sample, a back pressure is applied to the reservoir, and the sample is drawn back into the syringe. So this allows you to get a very large number of measurements with only a limited amount of sample. So this is particularly used for studies of shear stability, thermal stability, and it allows you to conduct larger rate and temperature sweeps with smaller sample sizes. So the last advanced measurement feature I'm going to talk about, so this is an example of a set of measurements conducted with sample retrieval. So we measured water-based viscosity standard at room temperature and a fixed shear rate, and we were able to conduct 50 measurements with a single 100 microliter syringe. And as you can see, the measurements for the same sample at the same temperature and same shear rate are all very consistent. The relative standard deviation of all of the measurements was about 0.15% of the average value, meaning that the measurements were very precise. So here's another example of one of the uses of sample retrieval. So in this study, water-based standard was characterized at 25 degrees Celsius, although this time we varied the shear rate between about 1,000 inverse seconds and 2,500 inverse seconds. And we got 80 measurements with only 25 microliters of sample. So using the sample retrieval functionality of the initium, you can get very high resolution viscosity fingerprints with a very limited amount of sample. So the final advanced feature I'm going to talk about is a combination of sample retrieval and automatic measurement mode to perform excuse me, an automated temperature sweep. So the automatic temperature sweep is set up by selecting different temperatures that you want the measurements, and using automatic mode to have the initium determine the appropriate shear rates to conduct the measurements at. And as you can see, we have presented the graphs for two different studies using the automatic measurement mode, or automatic temperature sweeps. So the first, shown by the black curve, is a water-based viscosity standard. And we measured the viscosity between about 15 and 70 degrees. And using a single syringe with only 50 microliters of sample, we were able to gain or to generate a very high resolution curve for the viscosity versus temperature. And as you can also see, the viscosity values agree very well with the reference viscosities provided by the manufacturer. So then in our second study, we measured the viscosity of a protein solution, BSA in water, between about 4 degrees and 60 degrees. And initially, the viscosity decreases with temperature as expected. However, around 60 degrees Celsius, the viscosity increases again. And this indicates that temperature-induced denaturation of BSA occurs around 60 degrees. And if we weren't able to perform an automated temperature sweep with retrieval, then we wouldn't have been able to get as many data points. So by being able to conduct this many measurements, we are able to pinpoint that denaturation happens at 60 degrees. So this is just one example of how the advanced features of the initium can be used to really understand the behavior of your sample very precisely. All right, so as a summary of the presentation, I gave a brief overview of VROC technology. I talked about why we needed, or what the need for automatic viscosity fingerprinting is. I reviewed the standard features of the initium, including measurements with small sample size, high accuracy, and high repeatability. And then I introduced the advanced features, such as automatic measurement, where the unit will determine the best shear rate for your samples automatically. Sample retrieval, where the sample is drawn back into the syringe after being tested, allowing you to get many measurements out of a small sample. And then the automated temperature sweep, which combines automatic measurements with sample retrieval to generate high resolution viscosity versus temperature curve. And then finally, I went over the applications of the different types of measurements. So thank you for tuning in. We will take a break for a couple minutes, but then we'll have some time to answer your questions.